Time feels like it has a built-in direction. I remember yesterday, not tomorrow. I can unbreak an egg only in my imagination. And the night sky shows a universe that was hotter and denser in the past, not in the future. So the question why time never goes backward is really two questions merged into one. First, why do the laws of physics mostly work the same if I run them forward or backward? And second, if the laws are almost time-symmetric, why does the real universe pick a direction anyway? Let me start with the part that surprises people. Most fundamental equations do not care about the sign of time. Newton's laws, Maxwell's equations for electromagnetism, and even the core equations of general relativity all allow processes that look valid when played in reverse. If I film two billiard balls colliding and I play it backward, the reversed motion still obeys the same equations. On that level, physics does not obviously forbid time going backward. So the never in never goes backward is not because the equations scream no. It is because the universe we actually inhabit is not just equations. It is a specific state of matter and radiation evolving in space-time with a very special history. The strongest arrow of time we know is the thermodynamic arrow. Entropy tends to increase. Entropy is often described as disorder, but that can mislead. In physics, entropy is about how many microscopic arrangements correspond to the same macroscopic situation. A gas in a box can be half on the left, half on the right, and there are vastly many microscopic ways to realize that. But all the gas on the left is a very special macroscopic condition with far fewer microscopic arrangements. If I start with gas on the left and remove the divider, the gas spreads out. That is not because molecules prefer the right side. It is because there are overwhelmingly more microstates that look like spread out than confined. So if I do not fine-tune the exact positions and velocities of every molecule, the system almost certainly evolves toward higher entropy. Now here is the key point. The microscopic laws can be time reversible, and yet entropy can still increase, because entropy increase is not a new law added on top. It is a statistical statement about typical behavior given a special starting condition. If I could prepare the exact microscopic state that corresponds to a movie of entropy decreasing, then the system would decrease entropy. But that requires extreme fine-tuning. It is not forbidden. It is just fantastically unlikely. So when people ask why time does not go backward, what they are usually seeing is that entropy does not spontaneously run backward in macroscopic systems. But that only pushes the mystery one step deeper. Why did the universe start in a low entropy state in the first place? If the early universe was hot and dense, that sounds like high entropy. Yet cosmology tells us the opposite. The early universe had low entropy compared to what was possible. The reason is gravity. Gravity changes what high entropy means. Without gravity, a uniform hot gas is high entropy. With gravity, a uniform distribution of matter is not the end state. Gravity amplifies clumping. Small density variations grow. Matter falls into potential wells. It forms stars, galaxies, and eventually black holes. And black holes carry enormous entropy. In fact, the entropy associated with a black hole, given by the Bekenstein-Hawking formula, scales with the area of its event horizon. For a given amount of mass, a black hole represents an extreme entropy configuration. So a smooth early universe, even though it was hot, was gravitationally special. It had remarkably low gravitational entropy because it was so uniform. We know the early universe was smooth because we can see the afterglow of the Big Bang, the cosmic microwave background. It is a nearly uniform bath of microwave radiation at 2.7 Kelvin today. When we map it precisely, we find tiny temperature fluctuations at the level of tens of microkelvin. Those correspond to tiny density fluctuations in the early universe. Those small seeds grew into the cosmic web of galaxies we see now. The fact that the early universe was so uniform is not a guess. It is measured. And that smoothness is one of the deepest reasons the arrow of time exists. If the universe had begun in a generic high-entropy gravitational state, it would already have been full of black holes and extreme curvature. There would be no long era for stars, chemistry, and observers to unfold. So I have one major ingredient: a low-entropy beginning, especially in the gravitational sense, creates room for entropy to increase. That gives a direction to time for everything from heat flow to memory formation. But I still have to connect this to space-time, cosmic expansion, dark matter, and dark energy. Because in modern cosmology, the arrow of time is not just about a box of gas. It is written into the history of the whole universe. Cosmic expansion is central. In general relativity, we describe the large-scale universe with a metric, a way of measuring distances in space-time. Observations show that space is expanding. Distant galaxies are on average receding from us, with recession speed proportional to distance. We infer this from redshift. Light emitted from a galaxy gets stretched as space expands, shifting it to longer wavelengths. We also confirm the expansion history using standard candles like Type 1a supernovae, standard rulers like baryon acoustic oscillations, and the detailed pattern of the cosmic microwave background. These are independent methods, and they converge on the same picture. The universe has been expanding for about 13.8 billion years, cooling as it expands. Expansion does not automatically create an arrow of time. The equations allow a contracting universe too. But expansion matters because it sets the stage for how structures form and how entropy can grow. As the universe expands and cools, different components decouple and evolve. Radiation loses energy as its wavelength stretches. Matter becomes dominant later. Atoms form during recombination. Photons stream freely, creating the microwave background. Then gravity takes over, and small density variations grow into the cosmic web. Dark matter is crucial here. It is matter that does not emit or absorb light, but it gravitates. We infer its existence from galaxy rotation curves, gravitational lensing, the dynamics of galaxy clusters, and the way structure grows from the early universe to today. In the early universe, dark matter began clumping earlier than ordinary matter could, because ordinary matter was tightly coupled to radiation and could not collapse easily. Dark matter formed the scaffolding. Baryonic matter fell into those potential wells after recombination. This is not just a story. It is tested by simulations that start with the initial fluctuations measured in the cosmic microwave background and evolve them forward under gravity. The resulting large-scale structure matches what we observe in galaxy surveys. That growth of structure is an entropy story. It is gravitational entropy increasing. The universe moves from smoothness to clumpiness, and then through stellar evolution and radiation, it produces enormous amounts of entropy in the form of low-energy photons spread through space. Now bring in dark energy. Dark energy is the name we give to whatever is driving the accelerated expansion of the universe. We discovered that acceleration in the late 1990s by observing distant Type 1a supernovae. They appeared dimmer than expected in a decelerating universe, implying that the expansion has been speeding up for the last several billion years. Multiple lines of evidence now support this. Supernovae, the cosmic microwave background geometry, and baryon acoustic oscillations. The simplest explanation is a cosmological constant, a constant energy density of the vacuum, which in Einstein's equations acts like a repulsive gravitational effect on large scales. But I have to be honest, we do not know what dark energy fundamentally is. We can measure its effects on expansion, and we can constrain its equation of state, which is close to -1, as expected, for a cosmological constant. But the microscopic origin is unknown, and the mismatch between naive quantum vacuum energy estimates and the observed value is one of the biggest problems in theoretical physics. So how does dark energy connect to time's arrow? It shapes the future. In a universe dominated by a cosmological constant, expansion approaches an exponential form. Galaxies not gravitationally bound to us will eventually recede so fast that their light will never reach us. The observable universe becomes more isolated. Star formation declines as gas is used up or heated. Black holes dominate the mass in many regions. Over extremely long times, black holes evaporate by Hawking radiation if our understanding holds. The universe tends toward a state that is cold, dilute, and high entropy. That is often called the heat death scenario, but I do not need the dramatic name. The physics point is that accelerated expansion and horizon formation push the universe toward a future where usable free energy becomes scarce. In that sense, dark energy does not create the arrow of time, but it influences the ultimate direction of cosmic evolution. It affects what the high entropy future looks like and how quickly the universe approaches it. It also introduces a subtle feature: horizons. In an accelerating universe, there is a cosmological event horizon, a boundary beyond which events can never affect us. Horizons have thermodynamic properties. They can be assigned a temperature and an entropy, similar in spirit to black hole horizons. This is not just metaphor. It comes from quantum field theory in curved spacetime. An observer in de Sitter space, the idealized spacetime of a pure cosmological constant, perceives a thermal bath. That ties spacetime geometry directly to thermodynamics. And it suggests that the arrow of time is not merely a property of matter in space, but is deeply linked to the way spacetime itself is structured. Now, if the fundamental laws are mostly time-symmetric, where does irreversibility really enter? There are a few places where time symmetry is not perfect. In particle physics, certain weak interactions violate CP symmetry, and by the CPT theorem that implies a kind of time reversal violation in specific processes. This is real and measured in systems like neutral kaons and B mesons. But as far as we know, that tiny microscopic asymmetry is not enough to explain the huge macroscopic arrow of time we experience. The dominant explanation remains the low entropy initial condition of the universe. So why was the early universe low entropy? That is where cosmology reaches its edge. We have models that describe the early universe extremely well, back to a fraction of a second after the Big Bang, and even earlier in some respects. Inflation is a leading idea, a period of accelerated expansion in the very early universe that can explain why the universe is so uniform on large scales, why space appears nearly flat, and why the primordial fluctuations have the spectrum we observe. Inflation also provides a mechanism to generate those fluctuations from quantum noise stretched to cosmic scales. The evidence for inflation is indirect but strong in the sense that it explains multiple observations with one framework. But inflation is not yet a complete theory. We do not know the identity of the inflaton field if it exists, and we do not know the full story of how inflation started or what preceded it, if anything. And here is an important subtlety. Inflation can make the observable universe look smooth and low entropy in some ways, but whether inflation itself explains the low entropy initial condition is debated. Inflation has its own initial conditions. It may require a special patch of space-time to begin. Some researchers argue it helps, others argue it shifts the problem. I want to be careful here. The arrow of time problem is not solved by saying inflation happened. It is an active area of research. Let me run a thought experiment that keeps us honest. Imagine I give you a universe in a random state, consistent with some total energy and the laws of physics. If gravity is present, a random state is not a smooth expanding cosmos like ours. It is more likely to be messy, with large curvature, black holes, and no long smooth history. Our universe looks like it began in an extraordinarily special configuration. Smooth geometry, tiny perturbations, and conditions that allow a long period of structure formation. That specialness is what makes a strong arrow of time possible. Because once you have that special beginning, everything else follows statistically. Entropy increases, records accumulate,